Hello everyone, does the sound work? Okay, so my presentation will be about Catalyst, which is a software for modeling biochemical reaction networks, or in principle, any kind of chemical reaction networks. The motivation is in biology, we have this big system of interacting components. 3 examples. The perceptive overview realized these are all examples from plants, and that's the kind of place I come from originally. But we have is that we have these big networks, and we're trying to figure out what to do. Best ways to model them. And one way to do this is to use chemical reaction networks. These model types are very simple. In principle, we have species, which is things of the system, and then reactions, which is things that can happen in the system. So here we have a couple of examples. We can have components X and Y bind to each other for a component XY. We have a dissociation, XY becomes X plus Y. We have degradation, X become nothing. Often these reactions have a constant rate, but you can also have that they depend on something. For example, you have a production of X activated by transcription factor. And in general, we have these reactions which is a couple of things becomes another couple of things. But what you then can do is that you take this complicated network and compose them to reactions. This is a network from the lysozyme stress response in bacteria. So on the left-hand side, we have this normal diagram where we show what's going on more graphically. And then on the right, I've kind of just listed the chemical reaction for. So on the top, we have the species of the system, the things we have. In this case, we have the molecule sigma V, which is in principle the response molecule. Then we have an RSIV molecule, which is a molecule which controls the response molecule under non-stress circumstances. And then we have the bound form. And we can also see that we have these 3 things in the diagram. And then I just list the reactions. For example, we have a production of sigma V and RSIV, the first one. We have a binding reaction, dissociation reaction, a type of cleavage reaction, and some degradation reactions. So we go from this form on the left, which is the biologists typically map up to us, and then we create a model like this one on the right. And what we often want to do is that we have a chemical reaction system. For example, here we have a single species X. It gets produced and degraded. We know some initial state of the system, and we want to know what happened to the system state with time from this initial state. And it turns out there are more or less 3 different ways to simulate the system. The approaches you can use the reaction rate equation, which is the main deterministic approach in ordinary differential equation. For some system, noise is important, and then you have the chemical Langevin equation and Gillespie algorithm type approach. And these both are noise approaches which takes noise into account, and in the chemical Langevin equation, we're going to have a continuous system, so we approximate the state of the system that we have continuous concentrations. On the right, we count the actual copy numbers of the species in the system. But what is nice with these approaches is that if we have a chemical reaction network, the simulation of these 3 approaches is ubiquitous. So this means that if we know our chemical reaction network, we also know how to simulate using the reaction rate equation, using the chemical Langevin equation, and using Gillespie's algorithm. And then the idea between Catalyst is there's some way to interpret the chemical reaction network, do something with them, and generate all of these approaches. So first, Catalyst, you write it in normal Julia code. And the first nice thing here is usually, the standard approach, you write your model in the form of equations. But for chemical reaction, if you, for example, have an ODE, you have an equation. But for the chemical reaction network, it makes more sense to store them in the reaction network form. So what you do in Catalyst is that you simply list the reaction events that you have. So if here we have a simple reaction network on the bottom, where production of X can bind to itself to form a dimer, it can dissociate, and we can have degradation of dimer, and then we simply list the reaction events here in Catalyst like this. And now what you can do is that if you have listed your events, so here we instead have a production degradation system, then you can use this as input to simulate all of these 3 approaches. So you only write your reaction network once, and then you can do the ODE simulation, the SD simulation and Gillespie type simulations. And what is nice is that Catalyst integrates very nicely in normal Julia code. So for example here, this is a simple workflow. We fetch the required packages, Catalyst, modeling package, differential equation for simulation, plotting package. Then we create a model using this macro. And that's, I should point out. So at reaction network, that's macro, which has to do with meta-programming. And this is basically what allows us to use this more specific code in Julia. So if you just wrote p, comma, nothing to x in normal Julia code, you get an error. But what this thing here, at reaction network begin ends, tells Julia is that here comes some kind of special code, and we have written a way for Julia to interpret that. And then you simply set your parameter values, your initial conditions, the simulation time. You bundle it up to, in this case, an ordinary differential equation problem. You simulate it, and you plot your solution, you get something like this. And all of this is very familiar workflow to us who use differential equations packet to simulate stuff. If you then want to, say, use the chemical engine approach, you instead create an SD problem, tell that we want to do an SD simulation, and use that one instead. And here's just an example I did. There are two advantages with, in this case, the DSL, which is this special way of inputting the models. There are other ways to creating the models, but I mostly focus on the special form right now. And here I have implemented the same model on the left using this Catalyst chemical reaction network form. I have done the ODE on the top right, and the chemical Langevin equation on the bottom right. And this is shorter, but I also think it's very nice because it's a more natural form to write it on the left, which helped me seeing when there's a bug in the code, when I made a mistake. It's also much easier to read the code and see what's actually going on, while if you have something on the right, the interpretation is much more difficult. We use differential equations for simulations. I mean, there's tons of materials that this is a very, very performant package when used with Julia. Here we compare to 4 other popular chemical reaction network simulation packages, BioNetGen, Copasi, Gillespie 2, and MATLAB's SimBiology box. On the top right, we just have 5 different models. On the top, we just simulate them until the steady state using performant ODE simulations. We see that Catalyst, which is the blue one, using differential equations, we have a 1 to 2 orders of magnitude better. On the bottom, we instead do Gillespie simulations. And here, instead of just doing a bar chart, where we simulate once to the steady state, we kind of run them for different time frames. So for example, this one, we run the model for 10, for 100, and for 1,000 time units, measure the simulation times, and then can we compare to the packages. And we see again 1 to 2 orders of magnitude performance increase. The reason on the right that we see much less lines is simply because the other package is not able to manage the largest models. So on the very left, we have a model around 10 species. On the right, I think it's about 4,000. We do a lot more than simulations. We're part of the SciML ecosystem. Simulations are a large part of it, but parameter fitting, bifurcation diagrams, finding steady states. I think there's some things that I added, not in this figure as well. But in principle, everything you can do in SciML, you can do for Catalyst models. And really, I think this is a nice summary, what you have in SciML. We have this modeling toolkit intermediate representation, which is how things set up. And I mean, we have had it mentioned quite a few times here today. But basically, the idea is that all of the tools for simulation analysis in SciML, they know how to work with the modeling toolkit intermediate representation. So if our modeling package can generate a modeling toolkit intermediate representation, we'll automatically get the entire SciML ecosystem working for a package. And I think this is a really nice way for people like me or Victor that do modeling software. Okay, we say we make our software jack into this intermediate representation. We get advantage of all of these tools. And the same way, if you make a tool, you ensure that the tool works in this intermediate representation, and you immediately support all of this domain-specific modeling. And also on the same note, chemical reaction networks, I come from biochemistry systems biology, where I kind of model what happens in the cell. But in principle, all things we have discrete species and discrete reaction events happen to the system, you can use these kind of models. So for example, here we have an SIR model where you have three species, susceptible individuals, infected individuals, and recovered individuals. And we have two events, one where susceptible plus infected become infected plus infected, and we have simple infected become, what's the R? Recovered, exactly. The recovered species. So work in progress. I just put up some things. We want support for better support for spatial simulations. So if you have something and you have like an entire tissue and you want to simulate the same things, these kind of things, we are mostly systems biologists working on it, but there's a chemistry community. Would be nice to have some support for that. I think the big one for me is like we kind of developed the package to like do the things that I'm interested to do, but I'm very small subset of systems biology. So it's kind of interesting, what do other systems biology, what kind of feature would you use for them? So I'd like to thank all the people who've been deeply involved in this, and I'd like to thank you all for your attention.
Thank you very much. Am I the only one who wants to see that SEIR model implemented in Catalyst using Unicode emojis?
Oh, we should do that.
That would be a great tutorial exercise. So, do we have questions from the audience?
So, like a general question, maybe also applies to what Victor presented. How much flexibility do you have in your package? So if I can like add new features of modeling, you know, so could it be done maybe by changing the code itself, or,
I think the question was how flexible is the backend for adding new features for the modeling. I'd say it depends on what kind of feature we're talking about. I mean, one thing that, like, if it's just like more flexible models, one thing we're doing now is a little bit is to kind of combine these reaction systems with just normal modeling toolkit equations. I think that's fairly flexible right now, so you can have like more like a physical equation. If I don't know how the temperature depends for the time of day, just picking something, and then creating these reaction systems. The other one is if you more tools for like working with these models. I'd say that we're fairly flexible, but it also depends. Like, yeah, it depends on the tool, but yeah, it's a little bit hard to answer without knowing specifically. But in principle, we're happy to accommodate as much as possible.
Any more?
So I was wondering, when you go from kind of the like RRE to Gillespie method, if you're in the kind of RRE, maybe you're using kind of units of concentration, but then with Gillespie, you're kind of forced to have like kind of integer counts, or I guess you could have kind of discretized concentration. So I was wondering how you kind of deal with the changing the units.
Yes, so right now in a single simulation, you only use one approach, you can't mix them. I mean, in principle, just go quickly back to where we do. I mean, the only difference, to be honest, is that we give the initial condition here, huge node, which is where you start the simulation. If you do a concentration simulation, so RRE or CLE, you can have any number, real number. If you do a Gillespie simulation, you would have to have an integer starting condition, so you can't start with like 1.2 of some molecule. But if you start with integer numbers, then that flows through to the entire simulation. So in that sense, it would not be a problem, no.
Okay. It would be interesting if like the parameters could have kind of units, because I sometimes notice that like when I go between the two things, I have to update the parameters by some like volume ratio or something like that.
Yeah. Sam, I think you can answer.
I can comment on that a little bit. So we support units right now, but we don't do automatic unit conversion. What we could do, or one could do on top of it, is write a unit conversion that takes a system and changes the units to generate a new system with whatever units you want that does those conversions for you. So like the same way that in modeling toolkit you can do like structural transformations on a system, you could make a transformation that takes a reaction system 1 unit and spits out the other. But we don't do any automatic unit conversion. We can do unit checking, but we assume you're giving us the model and the units you want simulated.
This is a question, I guess, about the broader ecosystem. So if you're like, I don't know, that's cool. But for like a tool like Cello, where you like specify the behavior and then you get back out a circuit, right? Like a genetic circuit. Do you have anything like that where you're tied in, where you say, I know I want this kind of behavior, help me back out like a chemical reaction that would have that behavior?
So I am not. So the tool, I should say, is I'm not familiar with it.
Oh.
But was the idea if you can kind of like go from a behavior then figure out the reaction network?
Yeah.
No, we don't have like. I think that would be a nice feature. I think there's some way to do it. But my general guess is that it's also a very, very hard problem to like, especially if you want to like find specific. But yeah, there's some. Yeah, no, not right now. It would be nice to have if someone wants to do that. Very encouraged.
Thank you for the talk. I was wondering, one of the things that I like to do with these reaction networks moving from like the mass action to the Gillespie is looking at how your parameters change. Like you define your propensity for your Gillespie algorithm, but you're talking about rates of reactions in an ODE. So have you thought about some way, like when you're doing the Gillespie, do you define a volume, first of all? And have you thought about a way that you could try to match, like if you run the Gillespie, is there a way that you could tell us what the corresponding rate would be for like the average behavior if we wanted to recreate it in an ODE setting? Do you know what I'm talking about? Like if you do the average, you define, if you do the work by hand, you can work out what the macroscopic equation would give you, and the average, the expected value would give you the approximation for, in terms of your propensities and volumes and stuff, an expression that would correspond with your rate in the ODE setting.
I think I vaguely understand, but I'm not sure if I dare to make a definite answer to that question. Yeah, I think you know a lot more about this than me, probably.
Any more questions? No? Thank you very much again.